Hey friends, how are you? I hope you are absolutely fine. I am Pratham. I am over here with my YouTube channel Learn with Pratham. Today I will discuss about spectral clustering, and already you know about the clustering. Clustering is basically a unsupervised learning, and why this particular spectral clustering is used to make the cluster to find the clusters in a graph space. So let's start and just we'll go through in this video, that is, what are the mathematical steps we follow to find the clusters inside a graph space using this spectral clustering method. Just you have to know about a little bit about linear algebra and eigenvalues, eigenvectors, this couple of things. Just you have to know about the basics of the linear algebra. Then that will be pretty easy to understand this spectral clustering. Okay, so what is graph? Graph is basically a collection of vertices and edges. Let us consider this particular structure over here. Suppose you do have 1, 2, 3, 4, 5 and 6. You do have 6 vertices and there are some connections between these vertices in this way. Okay, so there is a connection between 1 to 2, 1 to 3 and 2 to 3, 3 to 6, 5 to 6, 4 to 6, 4 to 5, 1 to 4, like this. Okay, there is no connection between 1 to 5, 1 to 6 or 2 to 5, 2 to 4 or 2 to 6, like this. Okay, so many cases you do not have the connections, and so many cases you have to have the connections. Okay, and consider this particular graph. This is a weighted graph. If that is not weighted graph, then just we'll take that weights are 1. Okay, but over here these are the weighted graphs. Okay, so this is a weighted graph, and for all these edges there are some weights. Okay, so fine. And this is a matrix representation of the graph. These are the 1, 2, 3, 4, 5, 6. These are the vertices, and over here also the vertices are there. 1, 2, 3, 4, 5, 6. All these vertices are also there. And what are the connections? And in just we have represented this particular graph in a matrix form. And what are the connections between 1 to 2? That is W12. Let us assume that value of this W12 is 0.8. Okay, so let us assume that W13, this W13 is 0.6. Okay, so in a similar way, W14, let's assume this 0.1, and just put all these some sort of values over there. Just I have taken an example over here in this way. And what is the connection between 2 to 1? That's similar to W12. That is also over here W12. So if we populate this whole entire matrix in this way, so what we'll get the structure of the graphs in a matrix form. Okay, so what is the structure over here in the graph? That is nothing but this is the graph, and you'll have the matrix of this graph structure is called the adjacency matrix, and you'll have over here, that is, all this diagonal will be 0. Okay, so this diagonal will be 0, and what is the and this is a symmetric matrix. The connection between 1 to 2 is similar to 2 to 1. Connection between 1 to 3, this is similar to 1 to 3. Okay, if there is a loop inside this, okay, let us suppose you do have a structure and you do have some loops, then you will surely get that there will be some value over there also. Okay, so in that case it will not be 0. Okay, so just I have not taken that example in this particular case, but just if you consider that, then you will have that in that case just that will not be populated as zeros. Okay. So what is a degree matrix? Degree matrix is nothing but sum over all these values. Sum over all these values will be taken care of over here. So this is a diagonal matrix. Okay. So what is the D11, D12, D22 to D2, D33, D34, like this. So what is this value? That is this is a diagonal value. So this is 1 2 3 4 like this. 1 2 3 4 5 6. Okay, so what is just this is a diagonal matrix, only the diagonals will be populated over here. Say what will be this value? That is the sum over this whole entire row. 0.8 plus 0.6 plus 0.1, that is 1.5. This is 1.7, like this. Just you have to populate this. Okay, so all these diagonals except these diagonals, all these off diagonal values except this diagonal, all will be 0. Okay, this is a degree matrix. So degree matrix, adjacency matrix is tells about the connection between the nodes. Okay, and degree matrix is that's tells about the characteristics of that particular node. Okay, so just after populating this degree matrix and adjacency matrix, what you have to do, you have to find this L. What is this L? L is the Laplacian matrix. So what is this L? That is degree matrix minus adjacency matrix. Okay, so from this you will get the Laplacian. After computing this Laplacian from the degree matrix and the adjacency matrix, what you have to find? You have to find the eigenvalues of this Laplacian matrix and eigenvector of this Laplacian matrix. The same for this L, you have to compute eigenvalues and eigenvectors. Okay, so you'll find when any graph you can take any graph with the positive weights. If you take, then you will find that the lowest eigenvalue will be 0 always. How? Just I will tell you just, and how it happens, just I will tell you just now. Okay, so your operation will start from this second lowest value. Okay, so each and every vector is connected to its eigenvalue. Okay, and these are eigenvectors. These are the eigenvectors you have to find of this Laplacian, and these are the eigenvalues. Each and every eigenvector is connected to one eigenvalue. So how it happens to be this lowest eigenvalue is always 0? How? Let's take this example. Okay, so let's take a simple graph between 1 and 2. Okay, this is W. Let us suppose this is W. Okay, so what will be the degree matrix? That is nothing but W W 0 0. Correct? This is your degree. Okay, so what will be your A? A is nothing but 0 0 W and W. Correct? If you connect, if you put W 1 2 over here, that is basically W, that is the connection between 1 and 2, and what is your W 2 1, that is also W. Okay. So if you find the D minus A, what will happen? So this minus this, so what will happen? So that is nothing but W minus W minus W W. This is pretty simple if you do the D minus A. Okay, that is your Laplacian over here for the simplest structure. Okay, so if you find the determinant of this particular matrix, then what will happen? Say, what is the determinant of this particular matrix? Say, if you have the eigenvalues over here, let us suppose lambda 1 and lambda 2. Okay. So what will be the lambda 1 plus lambda 2? That is the trace of this matrix. That is your 2W. And what is the determinant of this product? Pi over lambda 1 into lambda 2. What will happen? Lambda 2 equals to 0. Why? So if you take the determinant, say just if you are doing the row column operations over here, just if you are taking like this, okay, this column plus this column, what will happen? So that will be reduced into 0 0. Now find the determinant, that is always be 0. It means if the product of these eigenvalues are 0, it means there is one eigenvalue, the value is always 0 for the graph. Okay, there is one eigenvalue, that will be the that will be always 0 for this particular Laplacian. Okay, this is a pretty simple. Just you can take any graph, you can find any Laplacian. Over there, if you find all these eigenvalues, one eigenvalue will be always 0. Okay, so this one is always lowest also, and second eigenvalue is this one lambda 2. Okay, so all these vectors are connected to all these eigenvalues. The v1 is connected to lambda 1. Just this is not our area of interest. Just our area of interest will start from here. So let's take lambda 2 is the second lowest eigenvalue. According to that, just you have to take this v2. v2 is connected to this lambda 2. Corresponding v2 is the corresponding eigenvector of this eigenvalue. Just you have to take it. Okay, so from here, let us suppose for this particular structure, if you take this particular structure over here, if you take this particular structure d minus a, and if you find the Laplacian, just do it on your pen and paper, or you can use some sort of tools in Python, or some sort of some sort of packages like NumPy and all. Just if you simply find the Laplacian, this minus this, and after that compute the eigenvalues and eigenvectors, and find this lambda 2 and corresponding v2. Just I have taken this example from, and I have computed of my own, and I have just extracted this value over here to make you understand. So what will happen? So this will be the structure of this particular vector. Okay, so this is your connected to, and from these vectors all these elements are there. Okay, what are these elements? Let us suppose connect all these elements to its node. To connect this element to its node. Five, and this is a 6. Okay, so now you have you have connected all these elements of this particular vector to its nodes, and just you are bifurcating in such a way all the positives will go in one cluster and all the negatives, okay, will be considered in the another cluster. Okay, so just you have to bifurcate in such a way that all the positives will be clustered in one cluster and all the negatives will be clustered in the another cluster. Okay, so just you have to bifurcate it. Okay, so what will be the partition? That is nothing but this, say 1, 2 and 3. Okay, in this particular structure you have taken second lowest eigenvalue, you have taken the vectors, you have connected all these elements to its node. From this vector, this is a vector. Okay, so out of that you have extracted the positive values, negative values, and just you are creating a partition between this positive and negative. Just you are creating the bifurcation over here. So what will happen? Just you have taken that, just you had already seen that 1, 2 and 3 are the positive values. So 1, 2 and 3 will be considered as one cluster, and 4, 5, 6, these 3 vertices will be considered as the cluster 2, another cluster. Okay, so that is your bifurcation line, that is the partition. So just in this way, if you do it, just you will get all these clusters from here. Okay, so this is a method. So if you need more than 2 clusters, okay, just you have made one bifurcation over here. If you want more bifurcation, then you have to consider this lambda 3. Okay, so from here in the lambda 3, just what you have to do, that is that you have to consider this v3. From the v3 you have to do the same operation over here. Okay, correct? So just do it. Take this adjacency matrix, take this degree matrix, create this particular, for this particular example, just create all these things: adjacency matrix, degree matrix, create the Laplacian, and find all these eigenvalues and find all these eigenvectors. From this, just find v1, v2, v3, v4, and do it how many clusters you want, and create all those couple of things, and make the clustering, make the bifurcation, make the partition. Just do it of your own. You can use Python over there, that's very nice for your purpose. Okay, so in this way, if you consider the same way, okay, So if you have to consider lambda 3, and if you have to consider v3, and again same operations you have to do positive negative bifurcations, and you will make another more cluster v4. If you consider v4, then you will make another more cluster, like that. You will go so on and so on. How many clusters you want, you have to do it in the same way. Now NG Jordan West method, that's pretty similar to this particular method. That is the basically normalized Laplacian. How to normalize this Laplacian? That is reformed Laplacian, or the normalized Laplacian, that is d power minus half into L into d power minus half. D is your nothing but degree matrix. Okay, you can, from this D you can find d power minus half, and just if you multiply the matrices in this way, after that you will get this L dash. If you find this L dash, you will find that all these values of the diagonals will be always 1. Do it of your own, and just comment below you are getting all the ones for this L dash or not. Okay, you will surely find all these ones, you will get all these ones in the L dash. That's basically normalized Laplacian over here. And again you have to, what you have to do, you have to follow the same steps. To make the clusters. Okay, so you have to find lambda 1, lambda 2, lambda 3, lambda 4 for this particular matrix, and how many clusters you want. Let us suppose you want 3 clusters, so you have to go for, if you want 2 clusters, then you have consider only this. If you want 3 clusters, then this one only, just you have to operate on lambda 2 v2 and lambda 3 v3. You want 4 clusters, then you have to go up to v4, like that. Okay, so I think this is pretty easy to understand for you. Just I hope I have simplified the whole entire complex structure in front of you. And just comment below, did you enjoy that, you have understood or not, and did you understood or not, just comment below. Did you enjoy that video? If you enjoyed, then please hit a like button, press the bell icon and subscribe my channel. Just I'll be very happy, and that will be the next motivation for my next video. Okay, so stay tuned. Bye bye for this video.